Welcome to Carlton's Math Corner. Today we're going to be discussing least common multiple. To begin, make sure that you have a smile on your face and then you have your math journal as well as your vocabulary packet out. Well, let's begin. First of all, what do you notice? What number do you notice remains the same? Okay, so I hope that you said that you notice that each rectangle is increasing by 6 and the number that remains the same is 6. Okay, what is the area of each rectangle? So the first one is 6. Second one, 12, yep. Third one, 18. Fourth one, 24, then 30, and lastly 36. Now, what would be the next in this sequence? What would be the next area in the sequence? You are correct. It would be 42. Now, how are you getting these numbers? What are you doing to find each of these numbers? Okay, those of you that said, well, you're just adding 6 to each one, you are correct. Those of you that were thinking, hey, if I take 6 times 1, I get 6. 6 times 2 is 12. 6 times 3 is 18, etc. So then down here for 42, I would take 6 times, the next number would be 7. 6 times 7 is 42. Now notice the dot, 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 because I could actually continue this sequence infinitely. Now there's something special about this sequence. This sequence is actually showing me the multiples of 6. Notice 6 is what remained the same. The only thing that I'm changing is what I multiply it by. So 6 times 1, 6 times 2, 6 times 3, etc. So these are all called multiples. Okay, so a multiple is a number that can be divided by another number without a remainder. So like if I say the multiples of 6, one of the multiples is 24, well, it is a multiple because I can take 24 and I can divide it by 6 and I get an answer without a remainder, and my answer is 4. So 24 is a multiple of 6. Now, multiples, they go on infinitely because I can continue this sequence, infinitely. And so multiples of 6, oh my gosh, we could keep going and going and going. We just keep multiplying 6 by another factor or another number. What do you notice with these sequences? Is there anything that you notice that's in common among these lists of numbers? Okay, so let's start off with the red list. Well, here's what I notice. I notice that for 3, if I take 3 and I multiply by 1, I get 3. Then if I do 3 times 2, I get 6. 3 times 3, I get 9. And it continues all the way down here to 3 times 16 is 48. And then there's dot, dot, dot. So I am just assuming that the dot, dot, dot is because it goes on infinitely. So these here are multiples of 3. 12. Same thing, I could take 12 times 1, 12. 12 times 2, 24. And that 2 goes on infinitely. And then the last one in purple, this is 16. So 16 times 1 is 16. 16 times 2 is 32, etc. These are all multiples of 16. Do you notice anything that's in common among all 3 of them? You are absolutely right. The number 48. Do you notice that 48 is a multiple of all 3? And what that says is that 48 is divisible by all three of them. 48 divided by 3 is 16. 48 divided by 12 is 4. And 48 divided by 16 is 3. So 48 is divisible by all three of those numbers. That is called least common multiple. So least common multiple is the smallest positive number that is divisible by each of the numbers that we're looking at. So if I'm looking at three numbers, I'm looking for the smallest number that they all share, and that is divisible by them. Okay, do you notice that there is no other number, no other multiple that 3, 12, and 16 share? There's nothing before 48. 48 is the first number they share. Okay, and that's why it's called least common multiple, because least means we need the smallest number. Why do you think we need to find the smallest number and not the greatest number? Why wouldn't it be called greatest common multiple? You're absolutely right. Remember how I stressed that multiples go on infinitely. Well, how do we find the greatest common multiple if they just continue to go on and on and on? You're right, we can't. We can't find it. So we're going to actually stop when we find the first common multiple. So the least one, the smallest one that they all share. So this is one way that I can actually find the least common multiple. I can list all the multiples of each number, or as many as I need to find where they actually share a number. Or I'm going to show you also another method. Okay. Before I show you another method, I just want you to see the reason why these are all multiples. Let me just show you a visual. Notice they share this multiple because I can actually create a rectangle that has an area of 48 for each one of these using, like for 3, I can do 3 times 16 and I get to 48. 12, I can do 12 times 4 and I get to 48. And 16, I can do 16 times 3 and get to 48. So this is just a visual for you to see that we're trying to find the common multiple that they share where they're divisible by that number. Okay, and so let me show you another way to find least common multiple, because sometimes they don't share a multiple until, I mean, you have to go like into the 200s, 300s, 400s. Like sometimes you feel like you have to go on and on and on in order to find a number that they share and have in common. So I'm going to show you another method to help you find the multiple quickly. Okay, and so here's the factor tree method. And this method, if I take, let's say I want to find the multiples of 60 and 100. Well, we've worked with factor trees in the past. We've used these for prime factorization. So we're going to use them now for least common multiple. So what I did is I took 60 and I broke it into factors. So 6 times 10 is 60. And then I kept going because I can break 6 up into factors. I can do 2 times 3 is 6. And for 10, I can break it up into 2 times 5. Now I circled all of these, and if you recall from prior videos and prior targets, we circle these because they are prime numbers. They only make one rectangle and they only have 2 factors. That's why I'm circling them. So over here, I'm going to do the same thing with 100. So I'm going to do 10 times 10 is 100, and I can break the 10s up into 2 and 5. And I circled them because they are prime numbers. I can't break them up any further without using the 1 and themselves. So I'm going to leave it the way it is. Then what I did is I wrote out their prime factorization. So I looked at 60 and I asked myself, how many 2's do they have? Well, they have two 2's. That's why I put 2 to the power of 2, because they have 2 of them. There's 1 3, so I put 1 3, and there's 1 5. Now I did the same thing for 100. I put 2 2's, so 2 to the second power is 2 2's, and then there's 2 5's, 5 to the second power. So we're using powers so that we can shrink it and not have to actually write out 2 2's and 2 5's. We're kind of shrinking it, okay? So first step is factor trees. Second step is writing it out, like writing out a prime factorization. Then third step, we're going to find something that is in common. Well, do you notice that they both have 2 2's? Like this one has 2 2's and that one has 2 2's. So I'm going to write that down. They both have 2 2's. They share 2 2's. Now the other thing they have in common is this one has 1 5 and this one has 2 5's. Well, that means that they only share 1 in common. And so I'm going to write down 1 5. And what I'm going to do is I'm going to actually multiply this out. I want to see what it equals. Well, if I take 2 to the second power, that's 2 times 2, and then times 5, I get 20. Next, I'm going to find what is different. What is not the same between them? Well, if you notice, this one has a 3 and this one does not. And so I'm going to put a 3 down. That's different. And the other thing that's different is this one has an extra 5. Okay? And because it has an extra 5, that is also something that's different among them. So I'm going to write down one more 5. That this one, there's 1 5 that is different. And I'm going to multiply those together too to see what I get. So 3 times 5 is 15. Now what I'm going to do is I'm going to take this product and I'm going to multiply it by this product. So I'm going to do 20 times 15 and the answer is 300. This number right here is the least common multiple and I'm going to call it an LCM. It is the least common multiple of these two numbers of 60 and 100. Now, can you imagine if you listed all the multiples of 60 and 100? Do you know how long it would take to get to 300? It would take some time. Yes, you could do it. If you prefer listing it out and finding the number, that's fine. That is one method. This is another method. Okay, so looking at this word problem, and this is our last problem, it says Ling needs to buy paper plates, napkins, and cups for a party. Plates come in packages of 12, napkins come in packages of 16, and cups come in packages of 8. What is the least number of packages she will have to buy if she wants to have the same number of plates, napkins, and cups? Well, first of all, I notice that it says least number of packages. Whenever you're trying to find the least number of groups of something, that is a hint to me and to you that we need to find the least common multiple. We're trying to find where would they intersect so that I know how much of each that I would need to buy, knowing that they come in these packages of this many. Okay, and so I'm going to start off. Here's my numbers that I'm going to use: 12, 16, and 8. And I'm going to list them, and I'm going to do the list way. And if I list all my factors, I notice that the first thing that they have in common is 60. And so right away, I notice by listing their multiples that 60 would be my least common multiple. And I did a factor tree below, but I still get the same number of 60. And you can use either way, whatever works best for you. So you can do the list way or the tree way and you still get the same answer of 60. At this time, please complete these two problems of the day. and you may use either method. Thank you so much for joining me at Carleton's Math.